digested all the information.
Yeah, I thought we did too, and I thought we came in here and kind of shared it and digested, so.
Yeah.
All right, how big was this drain area? All right, so we're 20 feet by 20 feet, and we're 6 inches deep, right? Okay, and then I'll just go for overall.
Should I title this 62?
So this was parking lot runoff. Well, which dimension are you thinking here? So we got this dimension,
I'm talking like the whole thing, like parking lot.
not the whole thing. So when we were out there, we identified areas of the parking lot that went to a drain.
I mean, like, what should I title the sheet? Like parking lot runoff?
Yeah,
lab?
parking lot. Yeah, perfect. Parking lot runoff lab. Yep.
Want the dimension?
Yeah, if you got them.
Yeah, so from
This-
the long one.
Yep.
That would be. Hold on, I'm adding it up.
Or do you have it?
Yeah, 123 and a half feet.
Is that including the 20?
Yeah.
123.
Are you sure you have? Didn't you start at the bottom corner of it? I think when you started stepping. No, like how she drew it and what I remember was I started at the corner. That corner of the 2020 right there.
Here.
Yeah, that's
right
right
here.
I remember, yeah, okay, when I went from left to right, that's where I started, but when I went from bottom to top, I started on the top right corner of the 20. No, to the right. You did start at the top right? Yeah, I started right there.
And went this way?
Walked that way, and it was like, whatever, 103. Yeah, so 34 and a half steps, yeah.
Okay, so it was 103.
Yeah, 103 and a half
Yeah.
from that point to the edge. And then from that left to right, when it was like 42 feet.
Oh, the overall?
No.
No, here.
Yeah.
Yeah,
From
42
there,
feet?
42.
Okay, perfect. And we said an inch an hour?
You wanted to do a quarter inch and an inch. You wanted us to do both.
Okay, so quarter inch is when it starts to move. Yeah, and then an inch. Because we had this at 1 degree slope. And our goal was to determine if this was big enough, right? Before it enters the drain. So I think we're gonna say the drain is 6 inches tall also. So then we get this 20 by 20 by 6 inches of reservoir basically to capture this storm. And we're gonna do a quarter inch to see how much that is when it first starts moving. And then we'll do the full inch, which is the 100-year storm. Did I say 3 hours or just 1 hour? Okay, we'll just do 1 hour.
What are we finding?
So what you want to know is in both a quarter inch an hour and actually it was just a quarter inch, so that would be probably the 15 minutes. But anyway, for the 1 inch per hour will fall in this area and it'll drain to here.
Okay.
Okay, we want to know if this is big enough because this is what exists in our parking lot. So for the 100-year storm, is this big enough to actually absorb this water without going into the drain, which is really how we want those swales or rainwater capture systems to work. We don't really want it to exit into the runoff system. We'd rather have the ground absorb it. Keep it out of the rain drain system that exists. So not everyone had all the data or had all the procedures, so we'll just let this one come in on Wednesday, along with the next one.
So all we're doing, we're getting the not necessarily the flow, but how much.
Yeah.
Will be.
Just a quantity thing, yep,
Yeah, and
Yep.
then you get the area and the volume of the.
yep. It's really just a volume comparison is all this one is.
Wow.
The next one's more difficult, because that one's gonna be a flow comparison.
The next lab.
The next lab, yeah.
I'll think that.
Well, we'll have it recorded, so that'll work better for everybody.
Is that 6 inches of depth for everything or just?
Yeah, it's 6 inches all the way around, 6 inches for that. There's a drain pipe that sticks up in the swale. So in this swale or this low area, capture area, there's a drain pipe that sticks up 6 inches, has a dome to it, you know, with a kind of a screen. So if this overflows, it does have a place to go. It goes into that drain, but we really don't want that to happen. We want the system designed to accept the water and give it back to the ground.
So for the volume, we would just assume that everything is 6 inches.
Yeah. Yeah, and there's a bunch of plants in the thing too, like it's full of vegetation,
Yeah.
right? Which is gonna do some absorbing for us once this water comes in. But
By
we're,
design.
by design, for sure, absolutely. Yep.
Right, that's. We want to use the area of the 20 by 20 because the rain hits it, right? So it's kind of already.
Yeah, no,
collected.
you include that, absolutely.
It's already collected there, so the water doesn't have to move there, it's already there.
Yeah, so the inch an hour is gonna be over this entire area, right? It's gonna rain in the swale also. So this whole area sees the rain. So you do want to include that with your calculation on volume of water going into the system.
Yeah, and for the volume of water, it should be the cubic foot per hour.
Yeah,
Should be what
Yep.
it is.
I would do a cubic foot comparison.
Then if the cubic foot per hour is smaller than the thing.
Yeah.
we're told.
Yep.
Adding 83 cubic feet. So,
The 20 by 20 did.
well, yeah, with a 1/4 inch of rain. So do you still get the 1/4 inch?
It's incredible. It's a lot.
Do you still get the 1/4 inch work? Yeah, it was fine, it worked.
That's 1/4 cubic inch per hour and 1 inch.
Yeah, so the 1/4 inch is when all the water starts to flow. So we do that calculation often, just to see, okay, water's beginning to flow. What kind of a impact is that gonna make in the swale? And then the 100-year storm will put down an inch an hour. So then we want to see, okay, in the worst case scenario, is this thing gonna work? Like the 1/4 inch an hour would be what we would do if we were gonna do an analysis of, say, because there's a low area, right, that comes down that provides a trough for it to flow in. So maybe we were gonna calculate, like, are those two low areas big enough to take the 1/4 inch an hour of water that's gonna start flowing, right? You would use it for that. But we're not doing that. They were pretty big. I'm sure they accepted just fine. So,
And this is not including any of the fact that there were the plants in there that are gonna absorb the water.
right,
And
That's right.
Assuming that the drain itself. Would start receiving, we wanna
Right.
know, would this thing collect all the water before it has
Yep.
to drain?
Yep.
Okay.
yeah, so the theory is, if it collects and holds the water, then that vegetation will just help dissipate it. It creates a network system in the soil. It's not that the plants absorb the water, they do, but not much, right? They're not that big of plants.
Yeah.
But they've created a structure of soil that allows the water to go into the ground. Rather than if you didn't have any plants in there, it would just become hard packed or that
Yeah.
doesn't absorb. It basically would turn to not concrete, but pretty close. So that's why they That's why they put those. And I think it's very rooty vegetation they put in there, like grasses and things that, like, if you've pulled grass before, that structure is. Like you pull it and then like most of the soil comes with it because it's created this like mat that will absorb water. So. You're probably getting another full 6 inches of water absorption, that allowed the upper 6 to go in to the ground.
I would like to see how those work after it's been raining hard all day and see the water
Yeah,
going into
yeah.
the drain.
Yeah, if you walk on campus ever and it's just pouring, then walk over to them and you'll see the flow. Yeah, it's just going in and they work very, very well. The ground's really good at absorbing water, like, especially in our area, less so in other areas that aren't as,
Is there like concrete underneath there? So that it's
Uh-uh.
not,
no, that's
so then
what,
like, what was the whole point of us not wanting the water from our parking lots going into the dirt? Right, because you're like the oils from the cars and all that, and it's bad for the ground and bad for the fish. But then like we're literally putting it into the ground.
into the ground's good. The ground will filter it. Into a drain is bad.
Oh, okay, because then it goes into the river.
And then it goes straight in without any filtration at all.
Okay.
Yeah, so most of the contaminants, when it goes into the ground, gets stopped in the soil. It's not good for our soil, but it's better than, heading into the creeks and streams and then oceans. So, yep,
Like a landfill, we can accept the fact that that's gonna be bad for the soil right there.
Yeah.
Yeah.
yeah, it's like a freaking coffee filter is how it was explained to me. Like, you put your grinds, in your filter and you add water and out comes what you want, and the stuff you don't want stays in the coffee filter. So
Is the concept of the roots similar to how gutters will have the chains? And the water just stays with the chains?
Yeah.
The water will stay with the roots.
yeah, so it's a little different. I mean, vegetation does do that. It controls water flow.
Yeah.
Like if you have a sloped surface, you'll see that they spray it with grasses right away. Like when they cut a new road in, they'll spray it with grasses and try and get those grasses growing immediately. So then when the water falls, you don't get dirt sliding, right? The grasses, the root system hold that in place.
Yeah.
So that's true. I think that the chain on the gutters is just a unique way to keep the water volume concentrated. Like if you don't have a chain and you just pull your downspout off, it just goes, just like sprays all over.
Like the gutters
Yeah.
here.
Yeah, if you put a chain, then it tends to track that chain down and then you'll see a drain on the ground. So it's kind of just a clever way to control water free fall.
I just saw a video of that on Instagram the other day.
Yeah, it does slow it down too. So for what that's worth, All right, we good on this one? Got everything we need?
How do you get the 1 inch to hour per volume? Is it like 1 cubic inch or?
So you use your area.
Oh, so that's 1 inch over the whole area.
That's right. That's exactly right. So you're gonna take your area, multiply by an inch, and you're gonna get a volume. Yep, exactly. Okay, on this next one, you have like multiple things to do, so. This is a bigger lab. And this will be our last rainwater runoff lab. We'll move on from there. So I am recording this, so you can go back and miss this and get this first part. I'm pausing because there's an engineering meeting going on. I'm gonna let that meeting. All right, so the next one is gonna be a rainwater roof calculation. And we're gonna check several things. So let me just write out what we're gonna check, and then we'll kind of talk our way through it. So we're gonna go and check gutter size. And these are 5-inch gutters. That's what they're called, 5-inch gutters. So if you look that up, it doesn't mean they're 5 inches deep or 5 inches wide. It's just a call out for a gutter size. There are 4-inch, there are 3-inch, and there are 5-inch gutters. So just look it up and you'll get a profile and you can come up with an area. An approximate area is fine. We're gonna work with 1 inch an hour of rain. And we'll just do 1 hour. So that's how we'll get our volume. Our roof pitch is 12.4. So that sets up a angle that you can calculate. And actually this drawing is not to scale. That's closer to a 6. So really a 12.4 is pretty flat. I just happened to draw it kind of pitchy. Okay. But what that'll set up is a angle that you can calculate in degrees. Right? We can all do that because it's a 12.4 triangle. So you can just use your 12 and your 4 and like the tangent to get this angle, right? Theta. Everyone with me? Okay. For every degree, we're going to get 1 foot per second of velocity. So your standard sidewalk's like 1 degree slope, right? That's where we got the 1 foot per second. So if it was 10 degree slope, you'd definitely feel that. That's quite a slope. That's going to be 10 feet per second of flow. Not flow, of velocity, sorry. Okay, so whatever you calculate for the angle of your roof, that's going to set up the velocity of the water. For every degree, you're going to get 1 foot per second. It makes sense? So maybe we should calculate that because then we can just talk about it out. I'll just do it real quick. 12, 4, and tangent. It's like supposed to be the arc tangent, sorry. Anyone get a number?
Theta?
Yeah, so if you set up 412, right, it's the tangent, the angle equals 4/12, so it's going to be the inverse tangent.
70.
I think that's the,
Inverse tangent 12/4.
should be 18, yeah, for this lower one. For this little one, that's this one up here. If you did 4/12, so if you do 12/4, right, we want that smaller slope. 18.43 is what I get.
It's 71.
Yeah,
You did 12/4?
so, yeah, I did 4/12.
It's supposed to be 12/4, right?
So good.
It's opposite over at Dixie.
So for this one, yeah, but we want that lower angle because the roof pitch is going to be super flat. So we want this angle,
Okay.
Oh,
right?
gosh.
Yeah. We don't want this angle up here.
We have an opposite of the theta is 12.
We want see how we drew the bottom square or the bottom triangle?
Yeah.
Yeah.
We want,
We want this
Yeah, I
angle,
know. I got that.
412, right?
we want
Okay.
this
Tangent.
angle.
4/12,
Okay.
right.
Yeah, okay.
Yeah,
I was
yeah.
confused too.
That makes more sense.
Yeah.
Yeah, the other side.
Yep. So that sets up our velocity at 18.43.
So that would be 18 feet per second.
Yeah, 18.43 feet per second. Remember, that sets up how much water heads into the gutter. 18.43 feet of the roof. Right? I don't know how long this roof is. Maybe it's not even that long. So maybe then the whole quantity of the roof goes. But this is going to be 18 feet per second. So every second, right? Every second, 18 feet of the roof exits into the gutter. That makes sense? So if the roof is 13 feet long, then the whole roof is going to exit into the gutter. If the roof is 30 feet long, then only 18 feet of it is going to exit in 1 second.
And that's 18 feet up the roof.
Up the roof, that's correct. Yep. Yep. So that's how you get the 1 second volume that's coming into your gutter. And then how fast is it exiting? What's the velocity in the gutter? Yeah, foot per second. Yeah, unfortunately, we have gutters pretty flat. They have slope to them, but just barely.
So it's like easy on the eyes, or?
Well, it's the only, because you have your fascia board, right? So on a house, you have your fascia board that's usually, depending how long this run is, it might be 8 inches, which is actually 7.5 inches. That'd be a big fascia board, right? A lot of times they're just 2x6 fascia boards. So that means your little gutter, sometimes they're 4 inches, would be down low here, right? And up high here to provide some slope. I tried to draw some slope there. So if you actually look at a gutter on a fascia, it really should be lower where the drain is and higher where, I mean, if it's put on correctly, it's got to have slope, right? You don't want your gutter to fill. You want your gutter to empty. So that's all we can get. You know, you could put a 2x12 and then put a crazy slope on your fascia, but they don't do that. It looks terrible. That makes sense? Yeah. So you really only get a foot per second of flow. So that means if we have a foot per second exiting and we have 18 feet per second coming in, I mean, it's going to hold, there's going to be some backup there. So that's what we want to first check is our gutter size. Like, is that big enough for this situation? 1 inch an hour of runoff. And we'll do the same thing. We'll say it's a 1/4 inch buildup on the roof before it starts to flow. Right? Not the whole inch isn't going to fall on the roof and sit there and then I'll flow at once, right? So during our 1 inch an hour storm, once we get a 1/4 inch on the roof, it starts to flow. It's actually a little faster than that if it's a metal roof. And it's actually a little slower than that if it's a composite roof.
You
So
say 5-inch gutters, is that how deep the gutters are?
no, look them up, Google it.
Okay.
So they're classified as 3-inch, 4-inch and 5-inch gutters. So when you like order gutters, he's going to say what size gutters you want. You'll say 5-inch. That can mean that they're like 4 across and 3.5 deep. That's a 5-inch gutter. Like, I don't know where they get the 5 inches for sure.
And then how do we find the area of the roof?
You have the pitch,
Oh, yeah.
you have the 30 feet by 40 feet, and then you have a 2-foot overhang.
When you say 2-foot overhang, is that like,
That's both ends.
yeah, is that like 2 feet, like the roof just keeps going 2 feet?
Yep,
or is it like
that's exactly
2
right.
feet from the wall?
No, the roof keeps going.
Okay.
2 feet past the wall. So I could maybe draw that overhang in on this side if I was really good with my 3-dimensional drawing, right? So yeah, it sticks out 2 feet here and it sticks out, you can see it better in the back here. It sticks out 2 feet past the wall.
Oh, like.
Yeah.
40, like-
Yeah, also 2 feet out here, right?
30
And
length?
2 feet out here. But you don't need that. You just need this length here. Actually, you do need that. Yeah, so if you draw the profile, and different contractors do this differently, that's for sure. But here's your roof overhang, right? Here's a wall. Follow me where I'm at? Yeah, this should be the 2 feet, not lineal feet of the roof.
Yeah.
2
that's
feet
what I was trying to
past.
figure out.
So you'd have to, again, triangulate this to get this X distance to add to this distance that you calculate. To get your full roof size. Yeah. All right, so first thing we're doing is checking gutter size, right?
So 5-foot gutter, Google says it's 5 feet,
5 inches.
5 inches wide and 3.5 inches deep.
Okay, so it is a true 5. Perfect. And you can keep it simple, like it might have some slope to it, like I think gutters often look like, they have like, I don't know, some slope to them kind of thing, but you can just make it square or rectangular, just keep it simple. Some of them have, some kind of fancy curves to them. Don't complicate it, just make it an easy area to calculate. All right, so then we're gonna put a single downspout on it. Single downspout on our run. That's a long run for a single downspout. So that would be the second thing, is to check the downspout. Is it big enough? And again, you can look that up, downspout size. For a 5-inch gutter, I think that's standard. So you should be able to get a certain amount of volume flow rate out of this gutter, right? And then you're just going to check and see how it comes down the downspout, if there's enough area there in the downspout to accept that flow rate. And then the last thing you're going to do is you're going to size I'm going to call it a sump, or the catchment. And this is going to be the underground catchment, which is a requirement now. It can be above ground in planter boxes, but we're going to make ours underground. And we're going to make it 2 foot by 2 foot by however long you think it needs to be. So again, you're going to get a volume of water coming out of your downspout. We want to use the full 1 hour for this. For volume of water. So once you get a flow rate, your flow rate could be in, cubic feet per second. It could be cubic feet per minute, whatever you come up with. We're going to say that storm hits for an hour. And we're going to have to size this rainwater sump or rainwater catchment system. And the ditch is going to be 2 foot by 2 foot by some length.
Alright, so let's say let's say the gutter fails.
Yep,
right?
yep.
We don't have big enough gutter. When we go to part 2 to check the downspout,
Yeah,
you just want us to assume that the gutter works?
Yep, yep.
Okay. Let's see.
yep. Let's just assume that we add downspouts to make it work, and all of that's going to run. And both sides are going to run. Both sides would typically run to this system. Like you don't put one in each side. Yeah, no, it's a real deal. Oh, that's blurry as heck. Oh, there we go. And then just imagine doing the 150, subdivision. What kind of numbers you're going to come up with that. So we won't do that, but if we make this work for every home, then we don't have to, accommodate all that water that would run into some kind of piping system.
The area of the roof.
Yeah.
So you have 2 feet spanning over on the left and the right.
Yep.
We also have 2 feet spanning over the front and the back.
2 feet spanning over the front. Let's call this the front,
Oh, I didn't.
right? So 2 feet this way, 2 feet in the back, and then 2 feet on the eave. This is called the eave.
So from looking from the roof down, the building looks like it's 44 feet by 34 feet.
Like if you look straight down on a floor plan, yep, that's correct. It's not a true, like, I'm okay with that number, 34. I mean, the 44 is for sure right. But the 34 is not correct because the 2 foot is a X distance.
Right, and we want the-
Yeah. So if you want to be really accurate, you would actually calculate this distance, which is going to be longer than 2 feet to add to this roof, right? So. Questions? So gutter size first, like, can it accommodate this? 1/4 inch running at 18.43 feet per second into the gutter. Gutter is exiting 1 foot per second. So you could figure out like in a per second, like this is a dynamic fluid problem, but we're not going to work it that way. You're going to work it in like 1 second intervals. Hey, there's this much water in 1 second going into the gutter. The gutter has this much volume. Did that work or does that not work? That if it works, great. In that 1 second, also, there's a certain amount of water exiting the gutter, right? So you could do that balance to determine if it's going to accept it or not. I mean, the gutter does have a hole in it. A certain amount's going to leave in that second. So that's the first part. The second part is now you have a quantity that's flowing into this thing, right? Should be able to come up with the volume flow rate, and then you should be able to compare it to the amount of area that's available and see if that volume flow rate could exit going down. The velocity here can be much greater, right? So it takes water faster than it receives water. So that's kind of important to think about. What then? Then we have this flow rate coming through the pipe system. We want to double it. It's going to be the same on each side, so you shouldn't have any extra work to do over there. And then you have a volume flow rate coming into this, and you have to accommodate it once you get it. So over that hour, how much water is going to come in? How much area is needed to absorb it? There'll be some complexities when you go to work it.
Are we gonna need the flow equation for this? The two will they be?
Probably not. I don't think so. I mean, I think you'll have to make some assumptions along the way, like the flow rate down the downspout. That'll have to be an assumption, falling water type of thing. But I mean, a pipe that's vertical, you should be able to come up with a volume flow rate for that area. Come up with a velocity that you think water will fall at. I mean, you probably even could Google that and get the exact velocity of the falling water, and that'll be your flow rate of your downspout, right? And then if you look at the volume that's coming into the gutter, you should be able to make that comparison and say, oh, that's nowhere near big enough, or, oh, that'll take it easy, right? We're not going to add in like 400 leaves that complicate the system. At least in my house. All right, that's it. That's your lab.